How can architects and acoustic consultants consider both sound insulation and carbon footprint in building design? This is one of the questions that led to the study I presented this morning at the joint ASA and ASJ conference in Hawaii. My name is George Edgar from Marshall Day Acoustics in Aotearoa, New Zealand, and today I'm going to give you a summary of the study and its findings. Before we get into it, I'm going to explain a few of the key terms to help you better understand the results. LCA, or Life Cycle Assessment, is an environmental assessment of something, which considers multiple indicators. EPDs, or Environmental Product Declarations, are LCAs conducted to the rules of a product category. Upfront GWP, or Upfront Global Warming Potential, is a measure of the carbon footprint associated with the production of a product, reported in an EPD as mass of carbon per unit. An STC, or Sound Transmission Class, is a metric used to assess a building partition's sound insulation performance. Carbon emissions can occur across the lifespan of a building. This study only considered the upfront carbon from stages A1 to A3 of the LCA, circled in green in this heat map, because the later stages are specific to each building. The heat map shows the production stage has a large carbon footprint relative to the rest of the building's life, another reason to consider only upfront carbon. This study compared the upfront GWP and STC of a range of wall and floor constructions typically used in New Zealand buildings. 3 frame types were considered for walls lined with gypsum board, and for floors, a cross-laminated timber or CLT slab was compared against concrete. The GWP data was for products available in New Zealand. 3 wall framing types were compared: 90mm standard timber and 92mm standard steel frames, and a 70mm timber frame with steel channels on isolation clips. The last frame type is labelled timber and clips for simplicity. 15 different wall assemblies were considered for each frame type, using 1 to 3 layers of different types of gypsum board on each side of the wall. This graph shows the results, with upfront GWP per metre squared of wall on the y-axis and STC on the x-axis. Steel-framed walls are shown as blue dots, timber-framed walls as brown squares, and timber and clips walls as green diamonds. The graph clearly shows that standard steel-frame walls are the most carbon-intensive option. For a specific STC rating, there's always an alternative to steel with a lower upfront GWP. At lower STC ratings, timber frame walls appear to be a good option. However, above around STC 45 to 50, the upfront GWP starts to increase more for every STC point gained. For higher STC ratings, the timber and clips option is clearly superior, with lower GWP than standard steel and much higher STC ratings possible than standard steel or timber frames. This is due to the clips structurally isolating the gypsum from the frame. Next, CLT and concrete floor slabs with suspended ceilings were compared for their upfront GWP. These systems were designed to achieve STC 60 by altering the slab thickness and ceiling linings. For the concrete floor and ceiling system, 3 grades of concrete were compared with different compressive strengths and amounts of steel reinforcement. This graph shows the upfront carbon per metre squared for each system. All 3 grades of concrete had a higher carbon footprint than the CLT system. What is interesting is the GWP is heavily controlled by the amount of steel in the concrete. This is illustrated by comparing the large rise in GWP between concrete 1 and 2 from increasing the amount of steel reinforcement while keeping the same compressive strength. Then you can see a very small increase in GWP between concrete 2 and 3 from raising the compressive strength while keeping the same amount of steel reinforcement. This study revealed some clear patterns and implications. Firstly, achieving a higher STC generally requires more carbon. There's no way around it as more material is needed and this takes carbon to produce. This means the design needs to be fit for purpose. Is the specified STC rating really required, or can it be reduced while still providing acoustic comfort? Secondly, steel was the most carbon intensive to produce of all the materials considered. But using small amounts of steel to create structural isolation results in walls with high STC ratings for lower carbon cost. This implies a need to look at the project as a whole. For a design with modest acoustic requirements, timber is a good option. For higher acoustic quality, steel may be required to provide structural isolation. For buildings incorporating concrete, the amount of steel reinforcement significantly influences the embodied carbon. And that sums up the study. Does anyone have any questions?
We have a
Thank
few
you.
questions for you in the Q&A. The first one is from Maya. It is, what are the key factors that influence GWP, and are some factors weighted more heavily than others?
Great question. The key factors that influence GWP are the energy required to turn the raw materials into the end result product and the amount of carbon that's stored or sequestered in the material. If it's wood, then there's a high amount sequestered. For upfront carbon, which I considered, the energy required to produce the materials is much more heavily weighted. I actually took out the stored carbon or included it rather than subtracted it as per the Green Star New Zealand methodology because you only really see sequestered carbon benefit over the whole lifespan of a building, not really in that upfront stage.
All right. Thank you for going into that for us. Our next question is from Avery. Avery asks, do you expect this result to drive adoption of lower carbon materials in building construction?
I really hope so. So this study is part of a bigger drive to include a carbon calculator tool as part of an update to our sound insulation software Insul, and we're hoping that because that's used worldwide, that will bring a greater awareness to consultants around the world considering both carbon and sound insulation in building construction.
All right, so we can hope. And our last question then is from Anashay. Anashay asks, what types of acoustic requirements do green buildings typically have to adhere to?
So the most typical acoustic requirements around the world are the internal noise level in the room and the acoustic separation or the sound insulation. And the internal noise level also is affected by the sound insulation. So the main acoustic requirement is sound insulation, which is one reason why I considered that as the metric to compare. And then after that, you commonly get the reverberation time in the room or how much echo or how much sound is bouncing around.